Hello everyone, and welcome back to the Nuclear Waste video series. In this series, we are discussing potential ways to solve the nuclear waste problem, which, as we discussed in the previous video, isn't really that big of a problem to solve. Our first option for disposing of nuclear waste is deep geological disposal, which essentially means burying the waste underground in a safe location. Geological disposal is a great way of disposing of really bad video games, so why not nuclear waste? On the surface, geological disposal is fairly simple. You need to bury the waste in a safe, geologically stable rock formation. If you have a geologically stable rock formation and your waste is placed in containers that won't leak, then you're all set. However, if your spent fuel container corrodes, water intrudes, the radioisotopes dissolve in this water, and this now radioactive water leaches out into groundwater, then you can expose the public to radioactivity. Likewise, if a volcano somehow forms underneath your nuclear waste disposal site and blows it up, then your volcano will spread radioactivity that was in your spent fuel. In this video, we'll discuss the risk of nuclear waste leaking from a geological repository, what you need to do to keep the waste safe in a geological repository, and what repositories people have proposed so far. Now let's start by defining the problem. How long do we need to bury the waste underground? How long does it take for the radionuclides in nuclear waste to decay away and become stable? This chart by the International Atomic Energy Agency plots the radioactivity that is present in 1 ton of spent nuclear fuel as a function of time. It also breaks down which nuclides contribute to this radioactivity, and as you can see, cesium and strontium dominate the spent fuel's activity for the first several hundred years, after which americium-241 takes over, and then americium-243, technetium-99, and a mix of several other isotopes. Because radioactive decay releases energy, whatever nuclide dominates the spent fuel's activity is usually also responsible for most of the spent fuel's heat generation, and mitigating heat generation is something that engineers need to consider when they design a repository. Okay, so we see that spent fuel gradually becomes less radioactive over time, but when does it reach a safe level of radioactivity? What even is a safe level of radioactivity? This horizontal line represents the radioactivity present in naturally occurring uranium ore, and you could argue that this horizontal line represents a safe level of radioactivity. Uranium ore is naturally present in the ground, and it is not a significant health concern, so I would argue that the spent fuel is completely safe after it decays below the natural activity found in uranium ore. Nuclear waste's activity drops below this line after about 2,000 years, and to be completely fair, this uranium ore line is probably a little higher than it should be. It assumes that the uranium ore is concentrated into 1 ton of uranium ore without all the little bits of non-uranium containing rocks that would naturally be mixed in with the ore. So this line probably more closely represents the activity found in uranium yellowcake. However, yellowcake does not pose a serious radiological concern. Its activity is actually quite low, so perhaps this line is indeed a fair threshold for when spent nuclear fuel ceases to pose a radiological hazard. Okay, so we need to store nuclear waste for maybe 2,000 years until it becomes less radioactive than naturally occurring uranium ore. What kind of container would hold the waste during this time? Would we put the waste into those leaky 55-gallon drums that you see in movies? Would we just throw it into some hole in the ground somewhere? The answer is slightly more sophisticated than these options. Here's an example of a KBS-3 waste container, which is a technology developed by Sweden to contain spent nuclear fuel in a geological repository. The spent nuclear fuel, shown here with a dummy fuel assembly, would be placed inside of a solid cast iron container, which would then be sealed and placed inside of a thick, oxygen-free copper alloy container, which would then also be sealed and surrounded by a layer of bentonite clay in a repository. As you can see in this picture, these containers are not flimsy at all. They are made of solid metal, and they're designed to resist corrosion and prevent the spread of radionuclides in the environment. We'll discuss this more later, but these containers were actually engineered and designed by studying how naturally occurring radioisotopes move through rock underground over the course of millions or billions of years in the natural environment, and they were designed to prevent the migration of these radioisotopes. Here's another picture of another proposed spent fuel canister that was designed to store waste in Yucca Mountain. As you can see, a lot of care and detail went into designing this storage container, and it contains multiple engineered layers that are designed to prevent corrosion and the spread of radioactivity. And remember from last time, our spent fuel is a solid ceramic material that is clad in zirconium metal. Even after these massive, thick spent fuel canisters corroded, water would need to corrode through this zirconium metal and then dissolve the ceramic spent fuel before it could even start leaching radioisotopes through hundreds of feet of solid rock into the aquifer. Okay, so far this situation seems pretty good. We only need to contain spent fuel for about 2,000 years until its radioactivity is comparable with that of naturally occurring uranium ore, and we have these thick, insanely tough canisters that are engineered to hold the fuel for many thousands, if not millions or billions of years. It seems like scientists have addressed most, if not all, of the technical hurdles involved with storing waste in a geological repository. So what is our actual policy for disposing of nuclear waste in this kind of geological repository? To answer this question, we'll have to discuss Yucca Mountain, which I knew we would have to do eventually. The Yucca Mountain Waste Repository is a proposed geological repository and is probably the leading contender for disposing of nuclear waste in the United States. Yucca Mountain is located about 80 miles northwest of Las Vegas, and it lies on federally owned land next to the Nevada test site, which is the 1,360 square mile site where the US government conducted 928 nuclear weapons tests, including 100 above-ground tests. Yucca Mountain is pretty much in the middle of nowhere, and the fact that it lies in a desert means that there's almost no water present to leach through the rocks and corrode the spent fuel waste canisters. What's more, the rock in Yucca Mountain is also made of volcanic tuff, which usually does a great job of preventing water and radioisotopes from migrating any appreciable distance, and the waste repository itself is planned to lie about 300 meters below the surface. So again, this seems more and more like a perfect combination. We really don't need to store the waste for a very long time. We have these incredibly tough containers to hold the waste, and the proposed waste storage site is in a geologically ideal location that is far from any densely populated regions. So what could go wrong? Unfortunately, many things. Let's start this discussion by asking how long the Yucca Mountain Waste Repository is actually required to safely contain nuclear waste. Is it for the 2,000 years that our chart suggested, or is it for even longer than that? The answer to this question is a very long but very interesting story. Originally, the EPA set a dose limit of 15 millirem per year for the Yucca Mountain Geological Repository. This means that no matter what happened to the repository, members of the public couldn't receive more than 15 millirem per year of dose from any radioisotopes leaking out of Yucca Mountain. This 15 millirem limit is an extremely conservative dose. You receive approximately 15 millirem roughly about once every 2 weeks from naturally occurring radioactivity. Furthermore, annual radiation doses from naturally occurring radioactivity vary by about 350 millirem per year depending on where you live. So an extra 15 millirem a year is well within the natural noise of radiation doses. Honestly, I would take 15 millirem of dose or even 150 millirem of dose without batting an eye. If you've ever received a CT scan, then you've received several hundred millirem of dose, and really a few hundred millirem of dose isn't really a big deal. So the EPA required Yucca Mountain to adhere to this 15 millirem dose limit for 10,000 years after the repository closed, which is, again, kind of sort of around the point in time when the nuclear waste would become less radioactive than uranium ore. So 10,000 years, kind of makes sense. However, it's worth noting that the EPA regulates other types of waste to a much looser standard than this. Most EPA rules only apply for the foreseeable future, which is about 5 or 6 generations. So the EPA's 10,000-year rule for spent nuclear fuel and for the Yucca Mountain repository is by far its most strict regulation. I mean, the EPA doesn't even regulate greenhouse gases at all, even though they proposed some greenhouse gas regulatory limits around the end of May 2023. Nonetheless, the consistent theme we see of nuclear being regulated to a higher standard than other energy sources continues, and this theme is totally not something that I'm salty about. Anyway, a study by the National Academy of Sciences took issue with the EPA's original 10,000-year window for assessing the peak dose, claiming that there is no scientific basis for limiting this risk period to only 10,000 years, and that the maximum dose might not occur until hundreds of thousands of years after that. Therefore, the National Academy of Sciences recommend that the Yucca Mountain dose estimates and their risk models should be evaluated to the extent of the long-term stability of the geological environment, which is about 1 million years. In other words, we want you to do your calculations for as long as possible. A 1 million year regulatory limit kind of throws a wrench into things because of just how hard it is to predict how anything will act after 1 million years. Humans only harvested the wheel about 10,000 years ago, and 1 million years is 100 times longer than that. Neanderthals didn't even exist 1 million years ago. The earliest cave paintings are only about 64,000 years, so 1 million years is a really, really long time. This 1 million year limit is very conservative, especially given how much the fuel's activity will decrease over that time frame. However, opponents to Yucca Mountain probably want these limits to be as conservative as possible. A common theme with anti-nuclear organizations is that they try to stop nuclear power by making things as expensive or as difficult as possible. And honestly, their arguments are sometimes made in pretty bad faith. So in 2004, the U.S. Circuit Court of Appeals ruled in favor of the challenges to the old Yucca Mountain standard, thus requiring the EPA to adopt a 1 million year regulatory standard for Yucca Mountain. In response to this ruling, the EPA changed the Yucca Mountain dose limits to be a limit of 15 millirems per year for the first 10,000 years, and then a limit of 350 millirem a year from 10,001 years to 1 million years. The rationale for a 350 millirem per year dose limit is that you'll get about 350 millirem of more or less dose by changing where you move in the United States. The natural radiation background varies by about that much, moving from the East Coast to Colorado. The EPA argued that people in Colorado don't have higher cancer rates than people that live on the East Coast. In fact, they have much lower cancer rates. So a difference of 350 millirem per year seems pretty benign. So the EPA's argument actually makes a lot of sense. We haven't observed higher cancer rates in populations that get 350 millirem of additional dose per year, so this seems like a pretty fair limit. However, it is also somewhat interesting to note that nuclear power plants do not subscribe to this logic, and instead put a cap on the dose to the public of 1 millirem per year, which is essentially zero dose. Nuclear power plant regulation is notoriously conservative, and even though the proposed Yucca Mountain regulations make perfect sense, maybe even more sense than nuclear power plant regulations, it is worth noting that the EPA argued that Yucca Mountain should be regulated differently than nuclear power plants. In my opinion, both nuclear power plants and nuclear waste are over-regulated. The fact that Yucca Mountain has different dose limits than nuclear power plants irritates some people, both on the pro-nuclear and on the anti-nuclear side of the aisle. So the EPA proposed this new two-tiered set of dose limits, and they were of course met with a slew of lawsuits, challenges, and opposition. In 2008, the EPA ended up pulling this limit back a bit. They reduced the long-term limit from 350 millirems per year down to 100 millirems per year, basically because they wanted the limit to be just a little more conservative and a little more protective of public health. The 350 millirem limit would have also been fine, and we don't even know if the biosphere will exist and be habitable in 10,000 years, thanks to climate change, but the EPA felt that a 100 millirem per year dose limit was a compromise that was more appropriate. Which is fine, we can work with 100 millirem per year, this is all fine. Several organizations endorsed this new limit, and this is where we officially sit today. Scientists and engineers need to guarantee that the Yucca Mountain Waste Repository contains the waste sufficiently to satisfy these dose limits for 1 million years after the repository closes. I will note that all of these changes and challenges to the dose limits probably didn't help Yucca Mountain's credibility or inspire any confidence among casual observers. Even if you're making these changes in good faith and in compromise, like the EPA was doing, constantly changing your limits and regulations suggests that you don't have any idea what the safe limit should be. In my opinion, the initial 10,000 year EPA dose limits probably would have been fine, but the EPA was ordered by courts and they relented to pressure to make the dose limits more conservative. Again, this isn't a good PR look, But moreover, on the scientific side of things, constantly changing your target dose limit makes it difficult to actually design a waste repository. Ideally, you would want to know your target limits before you even start building and designing your repository. But one way or the other, we have these dose limits for the Yucca Mountain Waste Repository. As we now design our repository, we need to make sure that the radioisotopes from the spent nuclear fuel do not escape the repository and give people a significant radiation dose. But at least now we have a target. We need to guarantee that the spent nuclear fuel stored in the Yucca Mountain Waste Repository delivers less than 15 millirem a year of dose to members of the public after the first 10,000 years at Yucca Mountain is closed, and then less than 100 millirem per year from 10,001 years to 1 million years. So let's talk about how these radioisotopes could possibly escape the repository and give people dose. I'll start by discussing two of the main ways that radioisotopes can escape the repository. One, if a volcano forms underneath the repository and erupts, and two, if the waste containers corrode and radioisotopes leach into the groundwater. Okay, so I know what you're all thinking. What happens if a volcano forms underneath Yucca Mountain and erupts, blowing the nuclear waste into the air and spreading it all over members of the public? Just like how Mount Doom dispersed little pieces of Gollum ash all over the hobbits at the end of The Lord of the Rings. The area around Yucca Mountain has experienced volcanic activity in its geologic past, so there is a small chance that a volcano could form beneath Yucca Mountain. The probability of this occurring sometime over the next 10,000 years is about 1 in 100,000, and it's about 1 in 1,000 over the next 1 million years. So what would happen if a volcano burst through the nuclear waste disposal canisters, gobbled up the nuclear waste, and blew it into the atmosphere? Believe it or not, scientists at the Sandia National Laboratories actually simulated this scenario. They assumed that the canisters would have no ability to contain the radioisotopes during a volcanic eruption, meaning that the magma would eat completely through the spent fuel storage containers. And they also considered the effect of groundwater intruding and dispersing radioisotopes that weren't blown into the atmosphere and spreading them into groundwater. Their calculations estimated the radiation dose that the average person and that the reasonably maximally exposed person would receive for eruptions that took place either 10,000 years or 1 million years after the repository closed. The doses that they calculated are probably a lot smaller than you might have guessed. The mean dose rate that they calculated was about 1/10,000th of a millirem per year, which is absolutely nothing. You actually get that much radiation dose once every about 8 seconds from naturally occurring radioactivity, which is about as long as it takes me to finish this sentence. They also found that the dose to the maximally exposed person was about 10 times larger, about 1,000th of a millirem per year, which is again basically nothing. My understanding for why these radiation doses is so low is because it's actually quite difficult for a volcano to capture, distribute, and aerosolize a large volume of the spent nuclear fuel. And also, whatever spent fuel gets distributed into the atmosphere is diluted over a very large area, a very large volume of space. So to summarize, you really don't need to worry about volcanoes blowing up our nuclear waste or blowing up Yucca Mountain, which is something that 8-year-old me spent way more time worrying about than was necessary. Still, I'm glad that someone did these calculations. It's good to know what you need to worry about and what you don't need to worry about. And it also gave me the chance to make this Lord of the Rings joke. The second and main way that radioisotopes could re-enter our environment and give people a dose is if the waste canisters corrode or rupture, water creeps into the repository, radioisotopes dissolve in that water, and then that water leaks somewhere into groundwater. At first glance, this doesn't seem very likely. The Yucca Mountain Repository is located in a desert about 100 miles northwest of Las Vegas. It's not in a region that's exposed to very much water at all. The waste would be stored in Yucca Mountain about 300 meters below the surface, and the water table itself is another 600 to 1,500 feet below that. So water would have to travel a long way to get to the spent fuel, dissolve the canisters, the fuel, and the radioisotopes, and then travel even farther to reach the water table. Radionuclide dispersal is made even less likely by the kind of rock that makes up Yucca Mountain. This rock again is made up of volcanic tuff. Tuff contains many cracks and many fractures, which make the rock act kind of like a sponge. it's hard for radioisotopes that are dissolved in water to migrate very far because cracks in the rock, cracks in this tuff, make little dead ends for the water. On the other hand, if the Yucca Mountain region started to receive significantly more rainfall, and a lot of this water intruded and leached into the repository, then the cracked volcanic tuff would cease to act like a sponge and would instead provide pathways for water and radioisotopes to migrate towards the water table. Given that Yucca Mountain again is in a desert, it's very unlikely that enough water would penetrate into the repository to corrode the spent fuel casks and disperse radionuclides, especially given how much volcanic tuff hinders water movement. But in any case, this process would take quite a long time. What's more, the water table below Yucca Mountain is part of the Amargosa Valley, which includes the Amargosa Desert, part of the Mojave Desert, and Death Valley. Death Valley really isn't a booming metropolis, and in fact, the entire 900 square mile Amargosa Valley is home to only about 1,400 people. So even if radioisotopes made it into the water table, they would contaminate a very sparsely populated region. Okay, so how much radioactivity is likely to leak from Yucca Mountain into the groundwater? The good scientists at Sandia National Laboratories calculated this as well. In their studies, they first looked at the likely concentration of radium-226 and 228, the concentration of various alpha emitters, and the concentration of various beta and gamma emitters that could leach into groundwater. So what did they find? We naturally have about 0.5 picocuries per liter of radium-226 and 228 in groundwater, and the limit for radium in drinking water is about 5 picocuries per liter. These scientists calculated mean concentration for these isotopes from Yucca Mountain was a minuscule 1.3 times 10 to the minus 7 picocuries per liter, which is way below the limit. In fact, most of the simulations actually resulted in no radium from Yucca Mountain leaching into the groundwater. So okay, we're good on radium. Next are the alpha emitters. Alpha emitters are harmless when they're outside of our bodies. Alpha radiation actually can't penetrate the dead layer of skin that you have outside of our bodies, but they can cause problems if you ingest or inhale alpha emitters. We naturally have about 0.5 picocuries per liter of alpha emitters in groundwater, and the limit for alpha emitters in drinking water is again about 5 picocuries per liter. The Sandia calculations estimated that Yucca Mountain would contribute at most about 1 times 10 to the negative 4 picocuries per liter of alpha emitters, which is again way below the limit. So okay, we're good on alpha emitters too. What about beta and gamma emitters? The Sandia calculations estimated a mean maximum whole body dose of 0.06 millirem per year and a maximum mean dose of about 0.26 millirem per year to the thyroid from these beta and gamma emitters. To put this into context, drinking water commonly has a dose limit for beta and gamma emitters of 4 millirem per year. So these dose estimates are again way below this limit. They're not as absurdly below this limit as for the alpha emitters or for the radium, but they're still about a factor of 16 below the limit. To put this into context even more, you'll get 4 millirem of dose just from flying on an airplane. So even if these radioisotopes do provide 4 millirem of dose per year, which they're not, this radiation dose would not affect your health in any observable way. Now, thinking about these dose limits, and speaking only as a scientist who has absolutely no legal background other than the fact that I watched Better Call Saul, these calculations make the conversation and the debates about Yucca Mountain dose limits seem pretty silly. Yucca Mountain isn't even close to exceeding these dose limits, and in some cases it's below these limits by a factor of 1 million or more. So why did we spend all that time and money debating the dose limits? Your guess for this is probably as good as mine. I digress. We've shown so far that the dose from volcanic eruptions and groundwater intrusion is minimal. So how else can radioisotopes leak from Yucca Mountain? This figure shows a complete list of all the different mechanisms that Sandia National Laboratories considered for how these radioisotopes could escape the repository. So what could happen? Well, first the drip shield around the canisters could fail, which is the part that protects the spent fuel canisters from getting dripped on by any intruding water, which reduces the package corrosion rate. Next, the waste package itself could fail early for a number of reasons. Next, seismic events like earthquakes could damage the spent fuel canister or create cracks in the rocks that facilitate water and fission product movement. This could occur either by seismic ground motion or by seismic fault displacement. The Yucca Mountain region has some tectonic activity, so the repository is certainly going to get some earthquakes. But in general, the area's tectonic activity is too slow to significantly affect the repository over the next 10,000 years. In fact, the fractured volcanic tuff that comprises the repository rocks tends to reflect earthquake faulting and strong ground motion events, which minimizes the impact of these events on the repository. However, in September of 2007, the Bow Ridge fault line was discovered to run underneath Yucca Mountain and beneath an above-ground storage pad where the spent fuel would sit before being permanently sealed in the tunnels. This fault was discovered to be hundreds of feet east of where it was originally thought to sit, and this discovery led the Yucca Mountain designers to move this above-ground storage pad and several other structures a few hundred feet to the east. This is ultimately not a big deal. These were all above-ground structures, and the fault ultimately didn't affect the repository. Next, as we discussed before, a volcanic eruption could take place beneath the repository, and volcanoes could also strike back with igneous intrusion, which means that magma could bubble up into the repository and melt the spent fuel canisters, but not cause an actual eruption. With the canisters melted, there would be nothing to contain the radioisotopes and prevent them from interacting with any intruding water and slowly creep towards the groundwater table. This event actually contributes quite a bit to the possible radioisotope dose, but it was still only about 1 millirem, which is well below the regulatory limit. So together, all these different kinds of undesirable events will, on average, expose the public to about a third of 1 millirem after 10,000 years, and to about 2 millirem after about 1 million years. In other words, even after 1 million years, Yucca Mountain will on average provide less dose to the public than one airplane flight. These numbers are about a factor of 5,000 below the minimal level of radiation dose that has been shown to increase cancer rates. So even if these calculations are off, they're not going to be off by a factor of 5,000. So from a purely scientific perspective, Yucca Mountain appears to be an extremely safe and extremely effective method for disposing of our nuclear waste. So where does Yucca Mountain stand today? At the moment, construction has finished on the main Yucca Mountain tunnel, but the many offshoots that would house nuclear waste are not constructed, as you would need Nuclear Regulatory Commission approval prior to constructing these offshoots in these tunnels. In 2009, Secretary of Energy Stephen Chu stated at a Senate hearing that Yucca Mountain was effectively off the table and that the U.S. would need to investigate more advanced options for disposing of nuclear waste, such as using fast reactors to fission long-lived actinides, which is something that I'll discuss in the next video in this series. In 2010, President Obama formed the Blue Ribbon Commission on America's Nuclear Future, which was a panel of scientists, business people, and politicians that was tasked with exploring different options for disposing of nuclear waste. In 2012, the Blue Ribbon Commission delivered its report to Secretary Chu and outlined a comprehensive strategy for managing our nuclear waste. Several of their recommendations include that, number 1, the United States should undertake an integrated nuclear waste management program that leads to the timely development of one or more permanent deep geological facilities for the safe disposal of spent fuel and high-level nuclear waste. Number 2, geological disposal in a mined repository is the most promising and technically accepted option for safely isolating high-level nuclear wastes for very long periods of time. Number 3, nuclear materials that require long-term isolation exist, and our nation has benefited from the activities that produced them. There is no ethical basis for leaving the entire burden for providing their safe, long-term disposition to future generations. Thus, while subcommittee members hold different views about the potential for future reuse of spent fuel, we all agree that it is time to begin developing and implementing integrated, workable solutions that include interim storage and permanent disposal of spent nuclear fuel and high-level radioactive wastes. And number 4, a new single-purpose organization is needed to develop and implement a focused, integrated program for the transportation, storage, and disposal of nuclear waste in the United States. So in summary, the Blue Ribbon Commission concluded that we have a responsibility to dispose of nuclear waste, and that we should pursue a Yucca Mountain-like repository for disposing of this waste. They did not comment on the viability of Yucca Mountain or of any specific repository, just that we should pursue a geological repository. They also noted that we should develop a new governmental organization for implementing our nuclear waste policy, which is something that I actually agree with, but unfortunately has not materialized since their report. So in summary, the Blue Ribbon Commission concluded that we need to do something about nuclear waste, and they even outlined a strategy to get the ball rolling. But unfortunately, nothing has really come from this report. So moving on, in 2014, the NRC issued a report that deemed Yucca Mountain to be a suitable location for storing nuclear waste. And in 2017, Rick Perry, the Secretary of the Department of...
3 agencies of government when I get there that are gone. Commerce, education, and the, what's the third one there? Let's see.
Announced plans to reopen work on Yucca Mountain, but unfortunately the following bill died in the Senate. Next, in 2020, Secretary of Energy Mark Menezes stated that President Trump strongly opposes continuing work on Yucca Mountain, and in 2021, Secretary Granholm stated that the Yucca Mountain repository would not be part of President Biden's plans for nuclear waste disposal. So to summarize, the only issue in our government that has bipartisan support is that you should like, comment, and subscribe on this. The only issue that has bipartisan government support is stalling Yucca Mountain. And honestly, I'm actually okay with this. Our nuclear waste isn't going anywhere, and it's really quite safe at nuclear power plants. So there really isn't any immediate time pressure to solve our nuclear waste problem. Furthermore, I personally would like to see us reprocess our nuclear waste, and you can't reprocess the waste if it's permanently sealed thousands of feet below the Earth's surface. Okay, so now that I'm done discussing the elephant in the room about nuclear waste, Yucca Mountain, let's tie up some loose ends. First, is there anything that we can do to the nuclear waste to make it less likely to leach into groundwater? Yes, there is in fact. What we can do is we can vitrify the waste. Vitrification prevents waste from leaching out or somehow migrating away from the geological repository by first transforming the waste into a chemically stable glass. To do this, the waste is ground up into a powder, mixed with molten glass, which is usually borosilicate glass, and then poured into a robust stainless steel container where the glass solidifies. We know from samples of ancient glass that glass can be chemically stable for thousands of years, and turning the waste into a stable, water-insoluble glass, which again sits inside of a stainless steel container, makes it extremely unlikely that the waste would dissolve in water or migrate anywhere. Think of it like this. Say that you have a leaf that's made out of radioactive carbon that you need to dispose of. In its natural state, the leaf could just blow away and fly anywhere. However, methods like vitrification essentially take our leaf, put it into a furnace to burn it, and then take the leaf's ashes, carbon, and turn it into something like a diamond. This radioactive carbon from our leaf isn't going anywhere once it's compressed into a diamond. Diamonds are very chemically stable, and they're not going to let this radioactive carbon move anywhere at all. If you don't like glass, there are other processes that accomplish the same goal. Cementation turns the waste into cement, which is also very chemically stable, and more advanced methods like synrock turn the waste into a synthetic rock, which also has an extremely stable crystalline structure.
You will not down before me, Jarrell! Both you and them one day, Jarrell!
You can also combine vitrification with other methods for disposing of nuclear waste, which I'll discuss in future videos. Deep borehole disposal is another method that provides a slight variation on geological disposal. Instead of mining a geological repository and putting the spent fuel inside of there, deep borehole disposal places the nuclear waste in boreholes that are drilled deep into the Earth's crust. Unlike mined geological repositories like WIPP and Yucca Mountain that only place the waste 300 to 700 meters below the surface, deep boreholes are drilled into basement rock, as deep as 5,000 meters below the Earth's surface. This basement rock is the crystalline, extremely stable rock that sits just above the Earth's mantle and below all other rock in the Earth's crust. The majority of this rock is hundreds of millions, if not billions of years old. So once the waste is stuck in this rock, it's not going anywhere. Another benefit of deep borehole disposal is that you don't need to construct a mined repository. You just need to drill holes into the ground. This means that you don't need to worry about ventilation, so people can actually stand in the repository and place the waste inside of it. You just need to lower the waste down a big hole. Deep borehole disposal would certainly allow us to dispose of our waste with no chance of it resurfacing and causing any dose. However, it's probably not the most economic option. Some sources estimate that deep borehole disposal is about half the cost of a mined geological repository, but until relatively recently, deep borehole disposal was thought to be a much more expensive method for disposing of large volumes of waste than having a mined geological repository. Another engineering issue is that the waste containers would probably need to remain retrievable for some period of time, maybe 5 decades. So you would need to design your containers and your borehole so that they could survive and be retrieved for at least this period of time. This is an issue that engineers could certainly solve, but it is at least one more issue to solve. Nonetheless, companies like Deep Isolation are looking into deep borehole disposal for disposing of nuclear waste in Slovenia, and deep borehole disposal might become more economic and even more attractive if we can combine it with other waste disposal methods, such as reprocessing, which can drastically reduce the volume of our waste. Next, a variation on deep borehole disposal is to bury the nuclear waste in polar ice sheets. These ice sheets are several miles thick, so we would easily be able to dispose of the waste at a similar depth to deep borehole disposal. Groundwater isn't going to intrude into ice sheets and disperse the nuclear waste, both because of how deeply buried the waste is in these ice sheets, and because these are ice sheets. The water is frozen. You're not going to have liquid groundwater intruding anywhere. Furthermore, burying the waste in ice sheets avoids potentially exposing people to any leaking radioisotopes, because the poles are essentially uninhabited. There's nobody around the North Pole or around the South Pole to be exposed to this waste. However, one potential downside to this approach is climate change. What happens if these ice sheets start melting in large volumes? However, we probably have a lot more to worry about than nuclear waste if several miles of our polar ice caps melt. 40% of the US population lives on coastal cities, and melting the polar ice caps to this depth would put these cities underwater. Yes, if these ice caps melt, then the waste could perhaps be diluted in the oceans, which is something I'll discuss in a future video. But since people can't breathe underwater, radiation from nuclear waste is probably the least of our concerns in this scenario. One final legal concern to consider with ice sheet disposal is that the Antarctic Treaty of 1959 actually prohibits disposing of nuclear waste on the Antarctic continent. So trying to bury the waste in ice sheets hits some legal snags with international law. So to summarize, this video has explored several different methods for disposing of nuclear waste underground in geological repositories of different forms. We investigated how long the waste would need to remain underground for it to decay to safe levels of radioactivity, and we explored what would happen if things like volcanoes, or seismic activity, or water corrosion expose the public to the radioisotopes in our geological repository. In all cases, the technical problems associated with geological repositories seem solvable. We only really need to isolate the waste for several thousand years, maybe 2,000 years. And in the worst case scenario, the spent fuel would cause less than 2 millirem of dose to the public. So geological disposal seems very, very plausible. But let's do a thought experiment. What's the absolute worst case that could happen? Let's make things as bad as possible. Let's say that we bury our nuclear waste in a random location with no spent fuel containers at all. And let's say that we put our spent fuel in a blender first and grind it up and just dump it into this random hole in the ground. Let's also surround the fuel with groundwater to make the radioisotopes nice and mobile, and even throw in some volcanic activity in the area. What kind of dose would this result in? It turns out that this absolute worst case scenario has actually happened before, and we have a real-life example that shows how well radioisotopes are transported in an environment with no spent fuel canisters or containment at all. The example I'm talking about is the Oklo nuclear reactor in Gabon, Africa, which is a naturally occurring nuclear reactor that sustained a fission chain reaction nearly 2 billion years ago. Uranium is naturally about 0.72% uranium-235 and more than 99% fissionable but not fissile uranium-238. So reactor-grade fuel is usually enriched to about 3 to 5% uranium-235. However, because uranium-235 has a shorter half-life than uranium-238, natural uranium used to have a much higher enrichment than it does today. At one point in history, natural uranium actually contained so much uranium-235 that uranium deposits could sustain a fission chain reaction. This exact scenario took place in uranium ore deposits in the Oklo region of Gabon, Africa, where the uranium was actually moderated by groundwater that intruded around the ore. We first learned about Oklo in the 1970s when France was mining uranium from the Oklo region. They analyzed the region's uranium and they noticed something very strange, that the uranium ore contained lower levels of uranium-235 than they expected, and also that it contained trace amounts of fission products. They calculated that about 1.7 billion years ago, that uranium ore deposits in Oklo were moderated by some nearby groundwater, resulting in a natural, self-sustaining fission chain reaction. This chain reaction produced an average of about 100 kilowatts of power, which is approximately the energy consumption of about 80 homes, and that this reaction lasted for a few 100,000 years. So this naturally occurring nuclear reactor produced a ton of energy and a ton of fission products over a very long span of time. This natural nuclear reactor also had no engineered structures to contain the nuclear waste. So what happened to it? How far did it spread? Are the residents of the Oklo region suffering from a kaleidoscope of terrible cancers? Is the surrounding area completely radioactive and uninhabitable? No, in fact, it's the opposite. This paper, and this paper, and this paper all explore the mobility of fission products from the Oklo natural reactor. And they all found the same thing, that these fission products barely moved at all from where they were created over 2 billion years. Over this period of about 2 billion years, isotopes like ruthenium, palladium, and molybdenum barely moved at all from where they were created, while more water-soluble isotopes like cesium and technetium moved at most several meters from where they created before they were quickly absorbed by surrounding metal aggregate materials. Overall, these scientists found that there was no widespread migration of these fission products, despite there being no canisters to contain the spent fuel or the radioisotopes, and also despite the fact that there was also groundwater and volcanic activity in the Oklo region during this time. Only radioactive xenon and krypton migrated out of the fuel during this period, which only happened because these elements are noble gases that don't really form chemically bonds with anything. These noble gas isotopes are generally not a big concern when calculating doses, since they don't really form chemical bonds with anything in your body, they just float off somewhere and go away. I like discussing the Oklo reactor when discussing geological repositories because it shows how absurd the nuclear waste debate really is. Surely, if the Oklo reactor safely contained fission products for nearly 2 billion years with no engineered structures or containment and in the presence of groundwater and volcanic activity, then surely we can contain fission products in Yucca Mountain, an ideal location, for a period of 10,000 or a million years. This is exactly why nuclear engineers say that nuclear waste is not a scientific problem. It is a political problem. Scientists and engineers have shown that we have every reason to believe that a geological repository like Yucca Mountain could safely contain our spent nuclear fuel, but we have not developed a geologic repository purely because of politics. Although this situation is a little depressing, it really isn't that bad. As I will discuss in the next video, options like reprocessing and recycling our spent nuclear fuel offer a ton of benefits to society, medicine, and science. Yucca Mountain being a political quagmire is a little disheartening, but it opens up the option of using methods like reprocessing to extract even more value from our existing waste. I will discuss reprocessing, which is perhaps my favorite method for disposing of waste, in the next video. Thank you for watching this video. I hope that you enjoyed it and that you even learned something, and I will see you in the next video.